So this talk, the title is there a free lunch in imbalanced learning? I did this talk, or I designed this talk under the assumption that some of you may not know a lot about machine learning or what is the no free lunch theorems. So bear with me if you already know this. Also, I should tell you that this is very recent work, and this is the first time I'm presenting this. So I would very much appreciate your feedback and your questions, because I think there will be a lot of space for that. This talk is essentially a theory meets practice problem. It's based on the work that I did with Hugo Monteiro and Vitor Cerqueira, with Hugo Monteiro more on the theory side, and with Vitor Cerqueira more on the practice side. And basically, we came to conflicting conclusions, let's put it like that. And so this talk is about presenting the individual results, and then raising some discussion topics on what lies ahead. So as an outline, I'm just going to do a flash introduction to machine learning, explain to you what's imbalanced domain learning, strategies that I usually use in that field, and then the two questions that spawned the two journal articles that are at the basis and the core of this talk. The first question is there a strategy that we can use in imbalanced domain learning that is best? And the second one is, can data characteristics help us guide that decision? And then followed by discussion. The flash introduction to machine learning. The term is coined supposedly by Arthur Samuel. I think he was an employee of IBM at some point, had this very ambitious goal of having a machine to play a chess with him, a checkers, I think, at some point, and then evolved to chess, but basically under the auspices of teaching machines to solve specific tasks. Okay, so that's the general outline. A more canonical form, and don't be afraid if you're not from analytical fields, the idea in machine learning can be summed up as obtaining a good approximation to an unknown function. Probably, if these concepts are not very familiar to you, I'll try to explain them, but later on. But what we need to do machine learning is basically four things. So we need data, we need an objective, we need learning algorithms, and we need evaluation methods. Okay. And the underlying assumption that we always have is that there's some type of mechanism, unknown mechanism most of the time, that maps the characteristics of something to the conclusions of something. Okay, if I pick up a rock and I throw it, I don't know how far away, I can plot this using my height, the strength that I use, the weight of the rock, and if I was in a vacuum, I could use the trajectory, the trajectory laws in physics to calculate where the rock would land. So I would have some information that I could use, and I would have a function that would tell me what the final outcome would be, like the distance that the rock would travel. And in machine learning, what we do is we try to approximate these functions, okay? What we usually call models. And why is this important? Because so far we haven't talked about any type of rules or coding rules or specifying how they should behave or etc. Because with machine learning, what we get is the ability to learn without explicit programming. Okay, so what usually will happen is we'll withdraw rules from data that we'll use to predict or to analyze, etc. The future data or unknown data. In a nutshell, we can, and because this is important for later on, we can sum up almost in the entirety of machine learning as an optimization process. So what machine learning is the process of optimizing a certain evaluation method. Okay, this can be a sort of downer for a lot of people, but that's what essentially it boils down to. So we have a lot of things in common with sound engineers at Constant. And this is a good analogy to explain what follows, because in the practice of machine learning, what we're trying to do is to create approximations that usually combine these actors. So we have a learning algorithm. So these will produce statistical models, which are based in two things. The data that we provide to them, so the data that will explain a certain phenomenon, and a set of parameters that we'll have to fine tune. And this is how we get the best model possible. We will need to have a certain evaluation metric, which is basically our yardstick, and we'll knob away in the set of parameters, changing them and optimizing them towards getting the best possible result. So, common machine learning tasks include classification, regression, clustering, and classifying something as being, for example, fraud or not. Regression is basically finding a fit that in linear regression, for example, is a line that would best represent a set of data. Clustering is obtaining or defining clusters or groups of data that are the most homogeneous possible between them. And then there are a lot of other tasks and variations in supervised learning, one-class classification, quantification, etc. Here we'll focus on classification. The thing is, in the real world and real-world applications of machine learning, what we usually have is a mess. We have noise, we have regime changes, extreme values, anomalous events. There are people here that are familiar with like stochastic data streams and etc. and data drifts and shifts and etc. They would know very well about this. And so the real world defies all of these standard applications or standard definitions in machine learning, which lead us to the problem of imbalanced domain learning. This is basically what I've been focusing for almost the last 10 years. And what it is a setting of machine learning tasks where in specific conditions which are very common in real world scenarios. And there's two things that you can just keep in mind as a description of this type of tasks. You will find a very skewed distribution of data. So for example, when you look at fraud detection, intrusion detection, and a lot of things like that, you'll have very few cases of fraud and a lot of cases of normal behavior. And our objective in these tasks is not to predict each case as it was equally important or relevant to us. No, in fraud detection, what we want to do is to accurately predict cases that are underrepresented. So our focus, our predictive focus is on rare and extreme events. And this changes a lot of things, okay? And that's why it's considered one of the most pressing problems in machine learning, because its applications go throughout all of the sectors in terms of real world applications of machine learning. What strategies can we use? Basically what we're talking about, and let me try to sum this, is, if I would have to sum this in other words, imbalanced domain learning is the process or the tasks where you have to bias models towards a specific type of targets, okay? And so when you want to bias models, you have several strategies that you can use. The most common are these three data pre-processing strategies, which basically are applied to change the original data distribution before applying a learning algorithm. So basically trying to shift the attention of models towards a certain class. Then you have special purpose learning methods, which is basically picking up existing algorithms and changing their internal behavior to guarantee that they will be focused towards this underrepresented classes or underrepresented interval of values. And then you have prediction post-processing, which is basically you operate at the end of the pipeline, basically making the predictions or the process of defining a certain prediction or not, mostly related to when the predictions are made in probabilities, to make them more sensitive to predict an underrepresented class. So far, three takeaways. Relevance of imbalanced domain learning, very much known and common in real world applications. Evaluation criteria is essential. So it's probably one of the most impactful and important differences with respect to standard tasks. Then you have a multiple strategies at your disposal to test and optimize, and resampling strategies, which are the data pre-processing strategies, are the most common strategy by far. And this is true both in terms of research and academia and application in industry. This is the backdrop to what followed in our recent research. At some point, we made the question or posed the question of, is there a resampling strategy that's better than any other? Or even if there's a comparison that you can make between one or another strategy. The thing is, we tend to make a lot of assumptions in machine learning. I mean, generally, we do that. For example, if we were in a physical environment, I mean, in a room, I would probably ask you for concerning people that have experience with machine learning, I would ask you, from your experience, what's the best learning algorithm? Some of you probably would say random forest or something like that. And usually there's a lot of responses. The problem is we have a thing since the 90s in machine learning, which is the no free lunch. Okay, at least it was applied or discussed and proposed in machine learning in the 90s, 96. So, I mean, they started a bit before, but the papers, the original papers, are 96. And what is the no free lunch? Basically, we have this man to blame, David Hume, British philosopher, which had this extensive work in terms of criticizing the induction, and has this phrase from a book of his, a treatise of human nature, that it's important to read at this point for us to be at the same level. So that there can be no demonstrative arguments to prove that those instances of which we had no experience resemble those of which we have had experience. We suppose, but are never able to prove, that there must be a resemblance betwixt those objects of which we have had experience and those which lie beyond the reach of our discovery. Basically, that we cannot prove that the experiences that we have had so far will continue beyond our present. Okay, and this is what David Wolpert picked up I mean, since the beginning of the 90s, I think 89 until 96, there was a lot of discussion in these fields concerning this issue. But David Wolpert is the first to formalize it, which is the application of no-free-lunch in machine learning. And he comes out with two papers almost simultaneously, which is the lack of a priori distinctions between learning algorithms and the existence of a priori distinctions between learning algorithms. We will be focusing on the lack of a priori distinction between algorithms. The most important concept here is this worthy thing, which is off-training set generalization error. This is important because it's the most critical concept in translating the David Hume's idea to machine learning. And basically its definition is the generalization error for test sets that do not overlap with the training set. So it's basically test sets which you don't know, and you have no possible way of knowing if they correspond to the dynamics or regimes that you have seen in the training set, okay? So the obvious implications is that different regimes may govern the generation of training data and test sets. So a very big red flag. NFL theorems, so no free lunch theorems. The standard setting that given a certain cost function C, the question is, what can we say about this probability of having a certain cost given a posterior, the function or the description of the test set and the training set D. The thing is, okay, this is a standard setting, what we usually apply and use and assume. But if we look at this from the off-training set generalization now, there's no possible way for us to make any assumption concerning that function, that posterior, okay? So our probability function becomes just the probability of cost depending on the data that we have, the training data, okay? So any models that we might create using A, B, C, D algorithms will depend solely on the training data that is provided. So basically, we cannot make any assessments or a priori judgments as to how these models may align with the posterior, okay? So this obviously is a big problem for our typical approach of using things like cross-validation, estimation methodologies, and what's on. The statement of no free lunch includes this assumption, this big assumption, which is, let's say that we have a set F of uniformly distributed, they will be appropriately weighted, of target functions. Okay, so it's important, the part of uniformly distributed. And the theorem would basically state that for any two algorithms, there are as many priors where a hypothesis generated by an algorithm have a better OTS error than the other way around. So on average, they would be considered basically the same in terms of performance. This has been thoroughly discussed for, well, 25 years, actually, more than 25 years. The thing that we still haven't discussed is how no free lunch theorems meet with imbalanced domain learning. And this was basically what we wanted to do. So what's the impact of resampling strategies and that probability of cost depending solely on the data, given that when we apply resampling strategies and different resampling strategies, we will have a different data sets for training, okay? So first question, what is the impact that resampling strategies may have when they are applied to
Sim, não, tens que deitar.
Opa. And then we have the formalities. We just assume that we have a data set D as a training set, and we have two distinct different resampling strategies, the resampling strategy 1 and 2, and that F will be a set of uniformly distribution of distributed target functions and a certain learning algorithm. The question here is, what can we conclude by comparing these two probability functions, okay, that are here on the right, or in other words, which are more relevant and incisive? I mean, what a priori assumptions can we make as to the impact of either resampling strategy concerning the cost function C, okay? The argument that we made, we hope that it poses a sensible argument, is that the lack of information that we have in this situation also is very similar, if not equal to the situation that we had before, just concerning learning algorithms. So we don't have any a priori information that can tell us if a data set produced by resampling strategy 1 or the data set produced by the resampling strategy 2 will provide any sort of advantage between them. Okay, so what we state is that when we compare these two probability functions, there is no information that will allow us to decide between them, okay, concerning predictive performance. And then the conclusion here is that we'll have this on average equal behavior between the two concerning one algorithm. And then when we repeat this argument over a set of learning algorithms, we basically reach the final result as in the original one. So translating this, so what's the importance of this? The importance here is that if there's no grounds for us to a priori decide which preprocessing methods, which resampling strategies are best, then we have a lot of work to do when we want to apply them. You know, we should have a lot of work. We don't have any way to distinguish them, so we would have to test a lot of them, to test their hyperparameter and stuff. I should state that one of the motivations here is our understanding and our experience in noticing that both in academia and the industry, there are a lot of assumptions concerning which resampling strategies are best and which resampling strategies should be used to test when you're proposing new ones. So, but getting back to this, so what we did was we took a chance in trying to make an experimental evaluation of a theoretical concept which has an assumption that is difficult to replicate. Okay. But what we wanted to see was the general dynamics. I mean, if we could look at general behavior of the results and have a clear indication that we were going in the right direction and that there's no possible way of distinguishing the impact of resampling strategies. We have this experiment evaluation. I won't go into details. I will leave you the references for this, so you can dive into that if you feel like it. But in terms of results, so we compared hypotheses selected by each estimation technique concerning all resampling strategies used. Okay, so we use cross-validation to select to select the best possible model. We used anti-cross validation, which is basically selecting the model that had the worst validation score, and the random selection is basically selecting a random hyperparameter combination. And as you can see in this figure, you have some differences between the estimation techniques, and then you have some dynamics, equal dynamics between some of the strategy within each estimation technique. But what we observed is that there are differences and noticeable differences between the probability of practical equivalence, which is this blue part, and like of drawing, among estimation techniques. So they are very different, and this goes against the no-free lunch theorems. But we saw within each technique that some resampling strategies have a lot of similarity, and of course we observed that cross-validation technique has an advantage towards the remainder, but this is we assume basically because we're simulating the off-training set generalization error with the holdout strategy. Basically, you're taking out a part of the data and using that for testing, but there is no way to guarantee that that is doesn't have a overlap with the training data. Then the second conclusion would be that we observe that there's a probability of the probability of practical equivalence of drawing between hypothesis and oversampling strategies is very similar, and between all of the estimation techniques. And we also see that random undersampling tends to be very different from these other strategies. An important thing here is the dynamics of this. So if you see here, we made this test for an increasing number of data sets, exactly to see what their behavior would be, if the variance would grow, if it wouldn't, etc. And what we saw, and this is an important thing, is that growing the size of the dataset pool does not imply a higher variance of these probabilities, which is good because stability would be a good thing to verify no free lunch theorems, and they're associated with these big data set pools, not big data, but a big data set pool. Yeah. So the second set of results, we compare the best hypotheses per estimation technique concerning all the resampling strategies used. So basically, the best one of them in all estimation techniques against the global oracle, which is basically for each data set, which was the best one out of sample. And again, what we can see is that we have oversampling strategies that to the right have a similar behavior. Random undersampling still presents a noticeable departure from the other strategies. But there are two things here that are quite important. First, there is no way that we can guarantee that we're working with a uniform distribution. Actually, we basically are assuming that this is a non-uniform distribution of target functions, which is not what the no free lunch theorem requires. And then we are using this out of sample experimental scenario and not the off training set scenario that is required. And this leads us to our third result. Basically, what we did was trying to simulate this this uniform distribution of functions basically having generating samples from like 5, 10, etc. until to 100 of the pool size, and trying to get the most uniform samples that we could in those with those thresholds, and then to make again the same comparison of the best one for each strategy and the best one for like the globally per data set. And now the results are a bit different. So now we can see that the probability of draw, so of being practically equivalent to the best possible model within the models that we tested, which were 444. They are quite similar, not exactly similar, but they are very similar within the oversampling strategies, which are these 4, and random undersampling strategies. So basically, these are the conclusions. But a final conclusion is that, as we observe, there are no strategies that provide a considerable advantage or just distinct advantages in relation to all others, and that sorry, and no strategy has a greater than 50% probability of providing a better outcome. So, as it turns out, our key takeaways here would be that there is no compelling evidence. I mean, that there is compelling evidence that the no-free lunch theorems can be applied in this context of imbalanced learning tasks and the use of resampling strategies. That when we simulate towards these most general conditions in which the no-free lunch theorems are proven, we see that the similarity of probabilities between each strategy become more and more connected. But overall, in terms of the practice of machine learning, this suggests that there's no way around you selecting a diverse set of resampling strategies and optimizing their hyperparameters, which is very impactful in the performance of these strategies. Okay. There's a final takeaway here, which comes from the paper and also related to a contribution not on the same year, but really connected with the outcome of these no free lunch papers, which is the importance of providing insights into the assumptions or the domains in which we apply machine learning and etc., where we observe that certain resampling strategies actually provide an advantage. So the no free lunch theorems will never say that, or don't say that in a certain domain or in a certain task, for example, there's no way that you can have an algorithm that will always be the best. That's not it. What it says is that when you look at the bulk of possible problems, all of them, so the most general conditions, there's no way that you can say that a certain algorithm will be the best of them, simply because you have no way of knowing that, because you can't make an assumption on the posterior. Okay. This wraps up the first question. And the second question that we had, which is a different line of work, was, can we look at the data characteristics of the data sets and try to leverage that to choose which strategy would be best in each case? So a different approach to all. There is a simple problem at this moment. I mean, you just have too many resampling strategies to test. I mean, it's not tractable for you to choose like 10, 20 resampling strategies, a considerable hyperparameter grid for you to test, and combine that with the learning algorithms that you would have to combine them with and their hyperparameter settings. So, for example, we had 444 models tested per data set in the last one, and in this paper we tested 469 models per data set. So this already is a very high energy cost that we should be very wary of going into. But the first thing that we want to say is that there's just too many resampling strategies, and this causes a problem in terms of finding out which one is the best. And how can we handle this? To solve machine learning tests, you have to have a certain set of skills and expertise. And in the search for wider adoption, especially concerning application domain experts, like people that really know what goes on in a real world phenomenon or sector, there's a entire field, like topic of research that has been amazing for this, which is automated machine learning, AutoML, which is also very used within like the community that is an expert on this subject. So automated machine learning seems to us like a very good candidate for us to handle this problem of having a lot of options and needing to shorten it down. And basically, just short definition for automated machine learning. The goal is to develop approaches that will select and optimize these predictive models automatically. So we start from looking at what we have without that, which is basically we pick up a set of a big set of possible workflows, in this case, learning algorithms plus resampling strategies. We apply a grid search, which basically we will make a set of possible configurations for the combination of this learning algorithm and resampling strategies, and we'll evaluate all of them, okay? Now, this is a very big process, requires a lot of energy, et cetera, et cetera. So a difficult process and a demanding process. The solutions here that AutoML provides usually can be categorized in two areas. So hyperparameter optimization, or optimization based, which is usually the SMBO, so the model-based optimization, which is basically an iterative process of trying to get to the best solution. And then you have this meta-learning approach, which is basically what we had in our first question. So how can we leverage, how can we use data characteristics to guide this decision process? So our objective with meta-learning is to leverage past experiences. So past experience concerning the performance of the models that we have seen in the past, and accumulate this information and combine it with the characteristics of the data sets in which they were tested, and to record the performance of each solution that we tested. Meta-learning has a lot of applications. It's very well known. One of its more notorious roles is in, for example, discarding configurations that the meta models estimate that won't be very good. This is obviously a very interesting thing to have when you're trying to reduce your footprint and the time that you require for performing some machine learning task. And here what we propose is to leverage this idea of AutoML and meta learning to create what we called the atomic, so the automated imbalance classification method. This has two phases. So the first phase, like the development phase, simple. We picked up on 100 plus base data sets. Then we extracted meta features from it, like data set size, imbalance ratio. I mean, there's a ton of statistics that you can find in the paper. I have the reference at the end. And also what we did was to estimate the performance of these, of each of these possible solutions. So we have a hyperparameter grid, and we test all of these possible solutions. We combine and store all of this information, and we create a meta model. So a model that tries to link the characteristics of a data set, the hyperparameter configuration and solution that was used, and trying to map that onto the estimated performance, okay? So in a second phase, when a new data set comes in, what would happen is you would extract meta features, as we did in the first phase, combine that with all of the possible, so replicate that configuration with the added information of all of the models that we have defined and tested previously, and then to predict what their performance would be. Using that, we can transform it into a ranking and then use it, and I'll describe later on how we used it, to make short lists of methods that we would estimate their performance on the new data sets, making these processes very much faster and much less costly in terms of computational and energy costs. In terms of experimental evaluation, again, I'll leave you the reference. You can take a look towards the details. But here we only used one learning algorithm and then more AutoML solutions that are well known. So the first result was just a simple one, trying to find what's the variance, like the rank variance of each possible workflow that we're testing. So in this case, I think it's 469 possible workflows. So combinations of learning algorithms and resampling strategies. This is the top 100 and the top and the bottom 100. So the important thing here is that no single workflow has a consistent advantage over everyone else. So, for example, the best one has a rank over 100, okay? And you can see the variance that they have. So you can see, like, empirically that no one solution is clearly a candidate for any data set that might come to this method. Then we also see on the other end that several workflows do not present very good solutions, but there are some of them, even in the bottom 100, that provide sometimes the best solution or one of the best solutions, okay? So this is quite relevant for us because in order to automate the selection of workflows, I mean, just to automate the selection of workflows, if we manage to take all of this into account, this would be great. But the best thing here, and I want to stress this again, is the reduction, the significant reduction of competition complexity and energy costs that would be associated with this. Then we look at the particular resampling strategies. The question is, can we find a certain resampling strategy that dominates all other strategies? And here we start to have some different results, okay? The conclusions by looking at that seem to be that, seem to demonstrate that some strategies are likely or more likely to have advantages and dominance over others. And that advantage is basically their ability to approximate the best possible workflow solution. Of course, this does not reflect the complexity of parameter estimation. For example, in SMOT, important sampling, we're testing over 100 possible solutions, while in atomic links and random undersampling, we're testing much less, like 20 or 30 solutions. So there's an imbalance here in terms of the solutions that were tested and could be improved. So now we look to the results of the meta model. So the outcome of developing the entire first phase, the development phase. And the question here is, how many models can we use to obtain an optimal or pseudo-optimal solution with this method? So we see that, and our decision was basically to drop it at 20. You can see that solutions go up. But since the line of the 20, there's no big gap. I mean, we want to leave it as low as possible. So we decided on a threshold of 20, which basically says that the probability of drawing with the best possible solution would be roughly 70%. And we come to the final result, which is comparative analysis in out of sample settings against competing solutions. And here, now we have a comparison to all of them. And what we can see is that the atomic solution provides the best results, quite similar to some others. But they demonstrate supporting evidence concerning the ability of atomic to provide some advantages, and some advantages even over a set of other AutoML methods and other heuristics that are commonly used. So again, just takeaways: we have a lot of strategy. This is a very difficult thing to go around. There's a lot of interest in imbalanced domain learning in real world applications. So obviously there's a lot of interest in this AutoML solutions. And what we did was basically to demonstrate that it's possible to leverage automated machine learning and meta learning to get a solution that provides, at least experimentally, good results. But we just describes two opposing results, or some that would at least describe some contradiction between them. And so a good question is exactly where do we stand? So when we confront this theory and practice, we look at, for example, no free lunch in imbalanced domain learning, and we see that the most general settings, no resampling strategy is better than another one on average. But when we look towards the other side, we see that, at least empirically, we can look at the data, so that we sample like the training data and get to a pre-selection of resampling strategies that will have a best result. Basically, and here we start to end this talk. This is our general assessment without any real assurances. This is highly influenced by the assumptions that we put into our work. And there's a lot of points in terms of discussion that we can bring up. I mean, Hume and the criticism of induction has been discussed a lot, especially in like the philosophy of science. And this was a very cool discussion with Hugo Monteiro from
Não, desculpa, eu deixei de ouvir pelo menos.
No, we cannot hear you anymore. No, we cannot hear you. No, can you hear me?
Automatically, you will.
No, we stopped hearing you a while ago.
Sorry.
We stopped hearing you a while ago.
Yeah.
Yeah.
Awesome.
So we were at this slide where we talked about copper.
Yeah,
there. Yes. And this is where we stopped.
Yeah, I think
right.
Just stop. The mouse, the keyboard, and the headset. But you can hear me now, right?
Yes, now yes. Okay, but you have to resume here and then.
Yeah, okay. Just, I mean, there is a lot of discussion. I mean, the work that Hume did in terms of criticism of induction is still very important today. But there's been a lot of discussions in terms of like the philosophy of science concerning this like restriction where, I mean, you can't make any assumptions on the future. Of course, you can make some assumptions on the future, but you have to be very wary on how you build on those assumptions. Like you can come to some assumptions, and we do that as scientists, but you have also to be constantly very wary and to constantly confirm those assumptions to see if they are valid. Okay. And this is very important in terms of the practice of machine learning, because we see that very often. I mean, just because Hume provides us with a proof that you can't make any assumptions in the future doesn't mean that in the practice of machine learning, you don't often see that. Like you have regimes that continue for a long time or that are mostly stable. What you can't do is basically assume that it will be like that forever. And that's basically what we've been moving towards. Then there are practical exceptions for no free lunch theorem, which is basically, I can state just the most important one for me, which is an energy cost. When you punch in the energy cost of building machine learning models, you're already introducing a factor that will create a mess with no free lunch theorems. I mean, this automatically would state that, for example, some algorithms which are very optimization heavy would basically be left out because the cost of deploying such models would be too much in comparison to the others. Then even in automated machine learning, the results that we had were quite interesting, and we're still thinking a bit about that. But there's one important key issue here, which is the assumptions that we bring in to experiments when we use cross-validation method. Because what we're doing is basically mixing and mashing the data without any regards for the assumption that Hume had. For example, that the test set would have no overlap and could be defined by a very different regime than the training set. And when we are doing cross-validation, we're just pushing that away and saying and assuming that there's a continuity of data and there's no independence between the two of them. And so this obviously may provide the way for AutoML solutions to have some advantage and to be able to predict which methods may have an advantage just by looking at the data. Just a final note. I mean, what we came to is that no free lunch in AutoML has a sort of contradiction, but if we go up a level and we would have competing AutoML solutions, then our proof also would state that by comparing in those general conditions, all of the AutoML solutions, they would have tendentially the average, the same average behavior as any of them. So that's a really cool application also. So I'm just wrapping up. I mean, there's a lot of information here. I think we'll have the video, and I'll put my slides in my GitHub. They're fairly easy to find. These are the two papers that are at the core of this talk. So no free lunch and imbalanced learning with Monteiro, and work with Peter Sequeira concerning automated imbalance classification via meta learning. And yeah, that's it. Thank you very much. Sorry to take that too long. I was aiming at 45 minutes, but yeah.
Okay, thank you very much. It was very, very interesting, a very inspiring talk. Thank you. So any questions? Any questions or comments? You can just unmute your microphone and ask. Okay, so Miguel, go ahead.
Can you hear me?
Yes, we can. Thanks.
Yes.
I want to thank you so much for the interesting presentation. Much appreciated. It's been a long time since I've heard about NFL, and I came across it more in the search and optimization literature than actually in learning. So that was quite interesting. So one question that I have is whether your main findings, whether they would also make sense beyond the approaches, beyond resampling type of approaches, because I mean, as you mentioned yourself, so these are the main or mainstream, I meant